Good afternoon, everyone. I'm Zhong He. I'm from University of Michigan, and this presentation is for the thrust area number 3 for advanced safeguard tools and accessible facilities. So the way I think about it is, doesn't matter how you do the non-proliferation verification. You always need sensors. You can rely on human intelligence, but that's not the direct measure of the whatever weapons or special nuclear materials. So even the extreme concept of zero knowledge, you still need a sensor to get the information. So our thrust areas mostly focus on sensor development for gammas and neutrons and even lasers, but for detection of nuclear materials. So I used this slide during the UITI review a few months ago, is that our area is well connected to the real world. This slide just shows some examples that we were fortunate to get involved in the gamma imaging workshop held by IAEA during almost exactly a year ago, just after the last annual workshop of this consortium. So they invited 8 groups, 4 American groups, 2 French and 2 German groups, 2 British groups. They invited Japanese, but they did not go to test a number of gamma imaging systems. And you can see Aiden there from DOE. This is the cross-yard of outreach, and this is the Berkeley group from UC Berkeley, and that is our Polaris CVT imagers. In April of this year, we also be part of the American delegation attended a different you can say conference on nuclear security and safety. So they were organized so the first one was organized by the Safeguard Division, and second was the Nuclear Security Division of IAEA. That was a very good experience to understand what people are interested in new technology and how our technology could impact the nuclear non-proliferation. And so, as I said, this area has been focused on sensor development. So this slide highlights some of the achievements of Professor Sarah Posey's group. So they have been working on fast neutron-based multiplicity counters. You know, the way I know is there are 2 different ways to measure the mass of plutonium. One is rely on the thermal neutrons. You thermalize it, then you use thermal neutron detector, which is basically 100% efficient. But then the delay time during the thermalization has a very poor timing resolution, but you have a very high efficiency. The alternative approach is that you can do the multiplicity counting using fast neutrons. They have very good timing resolution because the fast neutron takes very little time to get to the detector, but then the efficiency is usually not as high as thermal neutron. So where is the trade-off? I'm not exactly in this area, but people have been developing alternative techniques, and their group has been using different fast neutron detectors. This is the commercial liquid scintillators, and this is the steel beam. To summarize their achievement, so they have pushed down. So this is the neutron and gamma signatures, because they can use a pulse shape discriminator to differentiate the signals between neutron and gamma. So they have achieved lower threshold, pushed down to about 400 keV, equivalent to a neutron recoil proton energy. What that means to the user is that the system could offer higher efficiency. And they have demonstrated that using their system, they can get higher multiplicative samples yield higher doubles count rate per, this is a long sentence, long count rate per unit single count rate. So what that means, I converted into the way I think this makes sense, is they can make more accurate measurement on plutonium mass because there has been, it's too technical, there's some deficit on the conventional technique that for high multiplicative samples, they tend to underestimate the mass. But these techniques show that they can more accurately determine the mass of plutonium, and they show that they can get about lower than 1% uncertainty in about 3 minutes time when the plutonium mass is between 50 to 500 grams. So what that means to the user is that they provided a faster technique that can potentially make the measurement faster to reduce the measurement time, or during the same measurement time they can get more statistics and get higher precision. So they have shown that even for unknown samples, some samples, can tell you what that is in the container, and for unknown samples they can also get below 2% standard deviation. And IEA recently stated that they plan to replace helium-3 based neutron detectors with liquid scintillators for fast neutron multiplicity counters. So that means their work is really right in the direction where the IEA is going. So the second group is based in Florida by Professor Jim Bartlett and Andreas there. So they have been developing new detector materials or compounds for detection of shielded nuclear materials. So they use liquid scintillators but put tin into the liquid scintillator. Why? Because liquid scintillators is known for fast neutron detection. But then after they put tin in there, tin has higher Z, so they can have higher stopping power for gamma rays. So the intention is the detector can detect both fast neutrons and thermal and gamma rays. And also they put gadolinium there to increase, it has a very, very high cross-section for thermal neutrons. So the idea is that they try to develop some sensor that can do both gamma, fast neutron, and thermal neutrons. And so there are some simulated spectrum, and they expect to see some peaks from the radiation interaction with their compound detector materials, not a single type of material. Move on. This is really a kind of out-of-box new technology that has been going on in Professor Igor Jovanovich's group, and he used to be at Penn State, and we are very fortunate to have him move to University of Michigan. So most of the group now are in Michigan. So they have been using, I just use my own word to describe the slides. So they have been using laser-based technology. So the idea is that you shoot a very intense laser and to heat up the sample, basically make a plasma of the sample, and then you observe the optical spectrum from that sample. The idea is that if you have highly enriched uranium, for example, uranium can interact with the oxygen in the air, and they can observe this spectral shift that can tell that they have highly enriched uranium shown in red color, or the depleted, or the natural uranium close to the natural uranium shown like the black, so they can see, that sample has highly enriched uranium there. And the idea is hopefully someday they can shoot from a kilometer away, shoot the laser and see whether there's a highly enriched uranium in some facilities on the ground, or from a standoff distance to detect this. And another key point here is that they demonstrated, the reason that this demonstration is important because the uranium oxide, the molecular isotope shift, is easier or larger than the difference between atomic samples like uranium-238, uranium-235. And so it's hopefully, my understanding is it may be easier to detect this shift if uranium. So the last slide, I tried to minimize the number of slides, but most of the individual research group will have posters and presentations on this, so I don't want to duplicate their presentation. So the last slide summarizes what our group has been doing over the last year. As some people know that we have been developing techniques based on the three-dimensional precision-sensitive cadmium zinc telluride gamma detectors, so that is our core technology. So I summarize our work into 4 parts done by 4 students. So the first one is David Goodman sitting somewhere there in the audience, and he has been studying some different image reconstruction, or you can say method or algorithm for quantum gamma imaging. So on the left here shows the actually the source is a ring, and but doing the image reconstruction using something we call the simple back projections. Like this is too technical, but each gamma event we detect, we plot a ring. So that's called simple back projection. We plot the ring. Then you cannot really see this is the source is a ring. So you can see this kind of a circular image. But using this we call SOE technique, that you can actually reconstruct the source image to much more close to the true image. And he has done simulations, and he has a poster that if you are interested, you can see. So what's the difference this with the conventional, like we do the quantum image using maximum likelihood, or we call the ERID, energy image integrated deconvolution, because those techniques, although in theory can do better, but they require very large computer memories to do the reconstruction. This one could be implemented on a chip for the field instrument. So that is why we are looking into alternative. Second part is done by Bennett Williams, sitting somewhere there. And so his thesis, PhD thesis, is focused on quantitative measurement of special nuclear materials using the high spectroscopic resolution and imaging CVT detectors. So we did some measurement in Y12 back in March. So we did we measured some disk samples of highly enriched uranium with different enrichment. And we have multiple sensors looking from different directions, and he has a poster, and he has been analyzing. The goal is to know the size, the shape, and the mass and enrichment of the sample. So if you are interested, you can talk to him and look at his poster. And Michael Stryker will give a short 5 minutes talk, I think, after mine. And he has been studying how to characterize the shielding material between the source and the instrument, say if the source is shielded. So what the 2 curves shows that we can actually determine the effective atomic number, say lead or steel or aluminum, and the total thickness, we call the mass thickness, independently. So this is a new technology, and he has 2 peer-reviewed publications this year about this technology. And he also has measured the fast neutron signatures during the measurement in DAF back in July. Then the last student is Stephen Brown, who is not here. And he has been working on a project we call the Black Box project, funded by DOE. This is not part of the CVT, it's a separate DOE program, but it will end in January of just in 2-3 months. Because he is wrapping up his thesis, and DOE cannot support it, continue to support it, but we think it's very critical to the mission of DOE. So the concept of the black box is that you don't know what's inside a container. You use the high energy resolution imaging capability, fast and thermal neutron detection on CZT to know what is inside the black box. As part of the black box project, we developed this thermal neutron imaging technique that using CZT, not using the traditional neutron detector. And as a demonstration, the demonstration was done by gamma ray source. So it's a continuous line, it's a tube, plastic tube, mounted inside a CD box. And you can see that we can image the gamma ray source to a scale of a millimeter. But he is building the neutron imaging instrument, and then we will demonstrate by the end of the year. To summarize, so IAEA is in need of new systems and techniques to verify compliance with the Non-Proliferation Treaty. This is one comment that before this consortium, when we talk to people about what new instrument you need for nuclear non-proliferation, often I heard, oh, we don't know, there's no need, all the detectors work fine. But actually, when we interact with IAEA, we learn that they are actually looking for new detector technologies for the future verification technique. And new techniques have been developed to capture the unique signatures of special nuclear materials. Like Sarah's group has been measured the plutonium field plates using fast neutron multiplicity counters, and Igor's group has demonstrated that they can actually see the isotope shift using lasers in their lab. And I just summarized the number of things that we have done in my group at the University of Michigan. So these techniques have the potential to improve the state of the art in detection of nuclear materials, counting and diversion. So I forgot one comment I was trying to make here, is that there's another activity not directly, one is that these two students, I should be honest, now these two students are not funded by CVT, but the measurement at DAF and some of the activities in Y12 were funded by CVT.
So that's kind of a puck of weapons-grade plutonium, and it's compared on this slide with high-purity germanium. So CZT is considerably more efficient